So until now, we have we have gotten introduced to the basic ideas of ABC, and we also seen how to do some adaptive ABC schemes. But you only saw, like you have learned that you have to, whenever you have been given a simulated data and observed data, from both of them, you extract some summary statistics, and then you compute a distance between them. In the talk Carlo gave, at the last point, we have talked, and Carlo mentioned that how do you get the summary statistics? Like you have a lot of summary statistics, and he used some sort of a linear regression to get summary statistics which is more informative about the parameters and things like that. And in the talk when Antonietta gave, she mentioned that it's very good to get the summary statistics and then the distance from the knowledge domain scientists. So like the people, like a physicist, he knows what summary statistics to be used and what distance to be used. But in real practices, when we have been trying to apply different ABC methods and algorithms, we have found out that, let's say, one weather problem, and there are like 3 meteorologists handling the same problem, and then all of them has come up with some different summary statistics. And like there is no uniformity. It's very objective. Like everybody can tell their own summary statistics. Everybody can come up with their own distance functions. And then methods like what you saw, the Farnham and Prangle, you have used linear regression. There has been recent methods where you use some random forest classification to find the summary statistics from them. So we started thinking about, like, is there a way to come out some sort of an automatic selection, like given all sorts of summary statistics. Let's say there are like 3 domain scientists. They give you 3 sets of summary statistics, and you put all of the sets together, and you find out the one which is the most relevant one, or the most informative one for your inference, or the distance function. Is there a way to do that? So towards that direction, I have these are works I have done with my collaborators in Helsinki. I moved here in 1 year before, but like this is an old work of mine. So there we were trying to utilize classification and machine learning for this kind of situations. How do you use those stuffs to choose the summary statistics, choose the distance functions, and things like that. Yes, so as we have started already, and you have seen that the likelihood-free inference, what I've been talking about, there are like 2 different variants. One is the approximate Bayesian computation. That's what we mainly covered here until now. For a review, I recommend you to check these papers. But here, what we will be talking about is classification, classifier ABC, where we use classification inside the ABC. I will come into that. And then the second approach is approximate likelihood. So you knew that in the whole ABC scenario, all the problems you are dealing, the simulator-based models, you don't have a likelihood function. So you don't have a likelihood function, and some people thought like, okay, why don't we just directly try to approximate the likelihood function and do some sort of things? So that's one of the other things I will talk in the second part of my talk, which is approximate likelihood. There is a work called synthetic likelihood approximation, and our recent work called L-Fire. I'll get into that. Both of them depends on the ideas from classification. So as a fundamental, the discrepancy measure, how to choose the discrepancy measure, we want to find a row between the observed data and the simulated data, or the summary statistics from Y0 and Y star, and we want to measure a distance between them. That's a main point of ABC. And how do we do that? So here we answer that by using an idea from machine learning, which is classification. If you're interested, this is a paper in statistics and computing from this year. You can have a look into there. But what is the basic idea? So we assume the sampling from the probabilistic model is parameterized by theta. So we introduce the model M, which is indexed by theta, and theta is our interest. And 2 data sets with very different values of theta are easier to discriminate than 2 data sets with similar values. What does it mean? That you can forward simulate. So let's say you have a theta 1 and you have a theta 2, and you've simulated from theta 1 and you simulated from the theta 2. But if your theta 1 and theta 2 are very similar values, like they're very same value, kind of like 0.1 difference, let's say, then you will think that the data sets will also be kind of similar. But if those are a bit farther away, they're very far apart, theta 1 and theta 2 values, the data set will be farther apart. So what made us to think about, so let's say you got a data set simulated from theta 1, and you got another data set simulated from theta 2. So this is data set x1 and data set x2. And if they're very similar, you're probably all familiar with the idea of classification. How many of you don't know what is classification? Okay, so classification main idea is that you have data sets coming from two classes, and you want to label them. So you want, and then you have a new data comes, you want to know which class it came from. But if you both these classes are jumbled on together, they're same, then it's very difficult to classify them. This is from 1 and this is from 2. But if they're very far apart, it's very easy to just separate them, right? So this is the classification task. So we can see that if theta 1 and theta 2 are very far apart, then classifying the two data sets are much easier than classifying if they're very close. So that's a basic thought we had, and we thought, like, why don't we use classification accuracy between data sets? And this is an example where these black dots are the observed data set, and this is a simulated data with mean 6, 0, and here simulated data mean half 0, where this was actually the true true parameter value. And you can see that, like, in this case, as I was explaining, the classification of these two classes are very easy, because they're far apart. But in this case, classifying them, I think you can do, but it's not obvious. And you will make a lot of classification errors in these cases. So classification accuracy in this case, classification accuracy virtually means how good you can classify between two data sets. That's the classification accuracy. And I will define how mathematically you can define that later. But so this is the main idea. But so we thought, like, if you can classify two data sets well enough, then use that as a distance. So more mathematical definition. So you have these y10 to yn0. So these are the n samples inside your observed data. And let's say these are y1 star to yn star. These are your simulated data. And then you create this whole data set and label them. Like these one have a level 0, coming from the class level 0, and label them as class level 1. And do a classification on them. And then see how good you can learn the classification rule. So that you can, so this is the definition of classification accuracy. You can see that gives you the classification accuracy, and you want to estimate this quantity. We use cross-validation and other methods to estimate the classification accuracy. I'm not getting into the details, just trying to give you the flavor. If you're more interested about the details, look into the paper. But so the main idea here is this thing is the proportion of correct assignments. If your proportion is very high, then you get a very good classification. And you need to think that whenever you have been given the classification accuracy, the lowest value is 50%, which is a random coin toss. Like you have been given a data set, the classification accuracy minimum can be 50, and its maximum can be 100% accurate. So going into more, so we propose to use discriminability of the observed and simulated data as discrepancy measure, and complete arsenal of classification methods becomes available to likelihood for inference. What does this mean? Classification is one of the fundamental thing in machine learning. If any of you have heard the term deep learning, what all the time you're seeing here and there, that's basically a classification rule. Like you get two complex data sets in some cases, and it's a nice method to do some sort of a classification. And then random forest ensemble and all sorts of different classification rules exist. So if you define classification accuracy as a method, as a distance measure, then this whole ensemble of classification methods become available for ABC. So you can use any of them to compute your classification accuracy, and you can use here. You can see this is like the same problem, what you are talking about, this mean 0, mean half. This is the probability distributions of them. And this black one is the true. And then if you have mean half, then they are very close. The probability distribution looks very similar. And if it is farther away, then they look different. And you can see this is the plot of classification accuracy, the discriminability. And you can see it goes down to 50% at the true value. So classification accuracy, CA will become 50% at the true value. Otherwise, it increases. So this is a very simple example. This is a Gaussian example. So we got a very good illustration. And these are more definitions about the Bayes classification rule and how do you use these different like all these possible different classification rules to learn the Bayes rule. Bayes rule is the optimum classification rule what you can learn. That's what the theory is based on, but you have to estimate. So if you think about deep learning, logistic regression, what you learn in any fundamental stat courses or computer science courses, these are all approximation to the Bayes classification rule. But you can estimate this quantity with cross-validation and all this stuff. I'm not getting into those details. I will show you some examples. So this is for some binary and count data. So we have a Bernoulli example. How many of you are familiar with Bernoulli distribution? OK, I see everybody. So it's a Bernoulli distribution, and we try to infer the parameter p. And so you can see that here we use all different classification rules, like this linear discriminant analysis, L1 logistic regression. Max rule is like you use 5 different classification rules and take the maximum classification accuracy for all of them. But like in this case, they all give kind of good result. And this is a Poisson distribution example where you try to estimate or get the posterior distribution of the Poisson parameter lambda, and then you get a result like that. Here, we don't define any distance. We just use the classification accuracy. And this is an example for the bivariate Gaussian distributions for mean and variance sigma, and then you get, this is a true posterior, and this is the posterior samples you get. And this is a time series with arch, and we get something similar. Now, this case, what we have done until now is that you got a distance measure, which is more like automatic choice, and then you can come up with all sorts of different classification rules, learn the classification accuracy from them, and take the maximum of them, and then you get the best classification accuracy, which is almost converges to the Bayes classification accuracy. Now, is there in this setup, can you do some sort of a summary statistics choice? Like, let's say you have a 10 or 20 or 30 summary statistics. Can you do some sort of a summary statistics choice? I will get into that later, but like one thing is I mentioned here, just like as a summary of classifier ABC, that ABC relies on the discrepancy measure, which is often chosen subjectively. So here we automate the choice. That's the main part here have done. But notice, if you have, any of you have been familiar with the classification rules, let's say penalized logistic regression, or the random forest, or deep learning, all of these rules are more successful because they can choose the features or summaries in the most efficient way. So if you give them 100 features, 100 summary statistics, they just chooses the best ones, which does the best classification. So in this case, if you just give them, like on those classification rules, all the possible summary statistics you have got, like you have collected from different domain scientists, it will automatically choose which summary statistics gives you the best classification accuracy. And all of these 3 algorithms, pen, log, reg, random forest, and deep learning, are able to do that. So in that sense, this is classifier ABC can do a summary statistics choice automatically, and also an automatic discrepancy measure. So it goes hand in hand. But we had faced one trouble here. Like all method is good in a specific scenario. So this problem faced one problem, is that you need to have 2 data sets to classify them. But in a lot of problems, your observed data has only one sample. And then you have one observed sample and a simulated data where you have 100 simulated data. Then it's an unbalanced classification problem. And so learning classification accuracy is a bit difficult. And then how do you use classification rule for those kind of problems for ABC scenario? We started thinking the first paper was already out, and so how do you solve these other problem? And that's why we came out with our new paper, which is towards the likelihood approximation. Then we said that, okay, ABC is good, but like, can we do something inside these other domain of likelihood-free inference, which is the likelihood approximation? And I go to the basic first. The basic was the Bayes theorem. You all seen this first equation of a Bayes theorem, that posterior distribution of theta given the observed data y is proportional to the, or is exactly to the likelihood multiplied by prior divided by the marginal of data set. And this is the fundamental Bayes theorem. And we start from there and we try to explain what's going on here. So as Carlo mentioned and we before mentioned, that most of the time measuring distance between two data sets is difficult. So we try to reduce the dimensionality of the data and we bring the summary statistics. So then it becomes this SY. This is the summary statistics. So this is the posterior distribution of theta given the summary statistics. And you can still use the Bayes theorem in this manner. And we know, yeah, it should be proportional to this thing. This is a mistake. I thought I corrected it, but anyway. So this quantity is unknown. So in this setup of the simulated based models, this likelihood function of SY is unknown, as because we have seen we don't know the likelihood function. So this group of scientists suggested, why don't we approximate the likelihood function of this quantity? Is there a way of approximating? So actually, what ABC, you have learned ABC. What does ABC do is implicitly approximate the likelihood function. So in the ABC scenario, you do this, like you have this real data set, and you have this YM star, which you simulated samples from the theta, right? Let's say you have sampled 100 simulated data. And then this is what you actually do in the ABC. You compute a distance between them. This is the definition. So you keep the YM star if this distance is less than epsilon, right? So this is an indicator function. And if this is your phi e, this is this indicator function, this summation gives you an estimate of the likelihood function inside the ABC scenario. So this part, you have been seeing it from the morning, that the distance between the observed data and then the simulated data is less than epsilon. And if it is less than epsilon, you keep it, otherwise you reject it. That's the fundamental idea. And that's the indicator function. And if you do it for 100 times, then this summation gives you an estimate of the likelihood function. And ABC does that inside the box. It's the black box we have as an ABC. It does implicitly. It does not do explicitly. It has an implicit nonlinear approximation. So in this paper, my collaborator Gutmann and Corander, they showed that it's a decent approximation, and this gives this probability of lambda theta less than epsilon given theta. If you are interested about look into how ABC goes for this approximation, you can look into these works. But in the more direct way of approximation, one of the classic works in this field is by Wood, Simon Wood, 2010 Nature paper. They looked into some ecological models, which is very popular. It's called Ricker model, modeling some animal evolution and then the growth processes and stuff. I'm not getting into the details. What they basically do, they try to estimate using a multivariate Gaussian distribution. So you have simulated these Y1 to YM stars. So you have, let's say, 100 simulated data from theta. And they are the summary statistics. Let's say you have 30-dimensional summary statistics. So you have 30-dimensional data set 100 times. And you can always compute the mean of that and then the variance covariance matrix, this thing. And that gives you a multivariate Gaussian distribution. What they do there is that they approximate the distribution of the summary statistics using that multivariate Gaussian distribution. And then they say that's a good approximation to the likelihood function for that. And literally, by doing that, if you have a good choice of summary statistics, like if you use Parnin and Frankel methods and some other ways, you actually, in this case, the synthetic likelihood works super good. And because it's a approximation of likelihood function, you can plug it into all existing MCMC algorithms like sequential Monte Carlo, Metropolis Hastings, all sorts of MCMC algorithms you can plug in. It's just like plug it in case of likelihood. There are theoretical justifications. Let's not get into that. And they showed that it works super good. And in a lot of examples, we have seen it works very well. But this has some restrictions. The first is that this is a parametric approximation of the likelihood function. In a lot of cases, the Gaussianity approximation would not hold. There's like a thin tail, and in their paper, literally, they come up with a recipe of 10 ways to solve these things. Those are very arbitrary and objective, and you can't really know in your problem how you do that. And then you need to give the summary statistics beforehand, like in all of the cases you have seen. So how do you choose the summary statistics? So in our work, we tried to choose the summary statistics in an automatic manner. And also, we wanted to remove that parametric approximation. We will have some sort of an approximation, but like you can still extend it to general forms. That's what we show. So the main part of our work is that we put the whole framework of the Bayes theorem as a density ratio estimation problem, and we try to solve that. So what is this? So you have already seen these equation, the Bayes theorem. You know that part. I don't need to tell it again. We just write it like that this is the prior, and this is the ratio r y given theta, where this ratio is the p y given theta divided by py. So I just like write this part as there's a ratio. You can do that. And we see that ratio is a ratio between two densities. That this is a density, this is the likelihood function, and this is a density from the marginal. So estimating r y theta is the difficult part since p y theta is unknown. So we don't know. But we know one thing, that we can simulate from py theta and we can simulate from py. So simulating from both of them is known how to do them, but if we know how to sample from them, can we estimate the density ratio? But okay, so let's say we know somehow how to estimate that, and if we can estimate this r hat y0 theta, this is the estimate of the likelihood function and posterior, right? You can just plug it in here, as because the prior is known, you get an likelihood function, estimate to the likelihood, estimate to the posterior distribution. Are you all with me? If any questions until now? Okay. So density ratio estimation is a very well explored area. One of the legends in this field is Sugiyama, 2012. If you look into his book, Density Ratio Estimation, so like tons of different methods. My collaborator Gutman also have worked on different algorithms. But like here we choose probabilistic classification as our choice. Like, as because we wanted to use classification somehow in these things. That's because we felt classification has so much potential, you can just bring it in. And probabilistic classification is one of the ways how you can estimate the density ratios. One of the basic methods we choose here is the logistic regression. If you have taken linear regression or linear models course in statistics or math or computer science probably, you probably all have seen logistic regression before. So the basic idea is that you draw samples yi star 1 from this distribution of the density function. And you like, this is the forward simulation part. And here also, you can use the forward simulation part also in a clever manner to simulate from these, and you can get these ones. Now, we know if you use a logistic regression, then the probability of y0 coming from the class, first class, or this first distribution is this equation. When h is unconstant, you don't have, what is this h? And we know from the logistic regression literature that if you compute this h hat, which is basically, this is a likelihood function of the class indices, and if you write the log likelihood and you take the rescaled negative log likelihood of this whole data set, and then you write jh and minimize that, you virtually get h hat. And like any statistical and mathematical softwares has this logistic regression solver. You will find it everywhere. So you can solve this h hat very easily, but also we know h hat is equals to log of p1 by p2. It reminds something, as because see, this is p1 by p2, which is py by theta divided by py in our case, which is the ratio we wanted to get. So virtually what you get, this exponential of h hat gives you a solution to the ratio if you can compute h hat. But okay, everywhere there has to be some sort of an approximation. So that was an unconstant scenario where h can be any function, and you come h in a general logistic regression scenario. But you have to restrict h to some class and then work on it. So for simplicity, we assume linear model for hy. So these are your summary statistics. So xi, yi, zeros, like we have seen all these different summary statistics. So you take the summary statistics and you assume your h has a functional form like that. And given that functional form for h, which you also learn. This is the thing what you normally learn in statistics. You try to find h hat. Given in that class, what is the h hat would be. So, and then you can estimate easily using all the, like the math and stat you have know. And then if you get the h hat, that gives you an estimate of the log p y0 theta and then this quantity. Okay? And that's because you can have these. You can easily get the estimate of the proportionally estimate to the likelihood function and the posterior distribution. That's the whole work stands on that. Now, see, as because you get an estimate of likelihood function, you can plug it in all possible MCMC algorithms, and you can do all the things. Now, as I was mentioning that this is an approximation, right? This h is a linear function. We are choosing as a linear function, so we do that. It's an approximation, but you can show in our paper, if you are interested, you can look into it. You can show that these thing virtually gives you an approximation of the likelihood function in the exponential family spanned by these summary statistics. If you're familiar with the exponential family, then it's a projection to the exponential family spanned by these summary statistics. So it's not a very trivial approximation like a Gaussian. It's a much more bigger generalization. But if you want to do much further generalization, you of course can choose. You can take a much more general function for h and then project it on some other class and things like that. But that's always a possibility. But this is a nutshell what we do. From prior, you simulate. So this is how we simulate from the P2 or the py part, which is in the numerator. So you simulate from the theta with like nm many parameters, and for each of them you simulate a data set. And this gives you from py simulation. And for the theta, you forward simulate and get 100 of them, or n theta many of them. And using these, you do a logistic regression. And this logistic regression give you an estimate h hat by minimizing. And this part you can use from any software you have. And it gives you a log ratio h hat, and then you have it, this is your true value, and you just plug it in this function, and this gives you an estimate of the posterior distribution. So in a sense, it gives you a direct approximate estimate to the, approximate to the posterior distribution. So this is the whole algorithm. We call it L-FIRE in nutshell. Okay, so now comes the automatic summary selection. Again, you have seen that HY we have chosen like that. As in penalized logistic regression, you just add a penalty term here. And then using that, you minimize the likelihood function. So what basically kind of plugs is the beta i's, where the xi or the summary statistics, which are non-informative, their value goes to 0, and others are kept. So in this way, in an automatic way, you remove the summary statistics. So in these scenario, I can get summary statistics from as many as scientists possible, and I can extend them, mix them, and like create a huge pile of summary statistics and feed in this method. And in this method, will pick up the most reasonable summary statistics, give me the best estimate it can create. So I don't need to think about the summary statistics choice if I have a big list of summary statistics, all possible summary statistics I can think of. So just to conclude this talk, I will use the Lorentz numerical weather prediction model, what you have seen in the first talk by Antonietta. I probably don't need to go through the model again. You had these two parameters, theta 1 and theta 2, and you just want to estimate that. And so you get a posterior distribution like that, and this is a base estimate of the true value, and then they're quite close. And it's quite a concentrated posterior distribution. You get the true value is on a very high posterior distribution range. For this problem, it's a quite and convincing result. And if you're interested in the comparison between the synthetic likelihood and these, you can look into our paper. There are lots more insights and how those things theoretically make sense and stuff. That's more or less this talk. It's like two ways of using classification in ABC or in approximate likelihood in the likelihood-free inference scenario we used. I think I will say most of the ideas kind of came from Gutmann, and we worked and developed and made these things possible. But we were quite excited too, because making it possible to bring all the classification tools like deep learning. We never used it, but like we can just see that you just plug in it deep learning in the scenario, it will work. But if it is needed, like it's maybe too of like a canon to use here. It's not really needed in most of the cases. But anyway, so this is the talk. I will conclude here. If you have any questions, you can please. Okay, that's.